Okay, so now that we have went through and gone over Reynolds transport theorem and material derivative and have a good understanding of how to connect Lagrangian Eulerian descriptions of control volume analysis and system analysis, we'll use the Reynolds transport theorem to derive the mass conservation equations for a fluid flow. Okay, so that's kind of the goal here. So first off, we'll rewrite the Reynolds transport theorem so that you have it at hand. So the Reynolds transport theorem, or RTT, was given as time rate of change of an extensive quantity of the system, which is given by B, is equal to the time rate of change of this quantity B inside a control volume plus the flux of this quantity B entering and leaving the control volume, which is the second term. Okay, so this was one of the forms of the Reynolds transport theorem. Okay, so we start off with writing the Reynolds transport theorem. Okay, so next step is to recollect mass conservation equation, right? Hopefully you guys remember what the mass conservation equation means, or what is even the axiom for mass conservation. Right, all that the mass conservation states is that mass cannot be created or destroyed. Okay, so you can't randomly create mass from thin air or destroy it, right? You can just convert it and transform it from one form to the other, right? So the total mass of a system always remains constant that you're looking at, right? So essentially what it says is that if you're trying to write this mass conservation in a mathematical form, all it is saying is the time rate of change of mass of a total mass of a system is going to be 0, right? Since the total mass, if there is no mass flux, right, it is if you have a closed system, right? Okay, and let's say it had certain mass m inside it, right? If no mass can enter or leave it, right, the mass inside that system that you're considering is going to remain constant over time, right? It's not going to change, right? It can deform, it can transform from, let's say, water to water vapor, but the net mass is going to remain the same, right, as long as it's a closed system. Okay, so that's the key element here, right? So if the net mass is remaining the same, if you're trying to find the time derivative of that mass, right, so if mass is not changing, the derivative of the mass is going to be 0 because the mass is constant, right? So that's essentially where this expression is coming from, right? That states that the total mass of the system is not changing with time, so it has to be 0, right? So one thing I always tell students, right, students seem to see mathematical expressions as abstract and just math, right? Mathematical expressions are nothing but just words being expressed, right? Instead of using words to express or describe a physical phenomenon, you're using math to describe the physical phenomenon, right? So it's easier and it's faster for students to understand concepts if they can understand what each term in the mathematical expression means, right? So like we said, right, this expression here is stating not all that it is doing is stating that the mass of the system, right, is not changing with time because the time derivative of it is equal to 0, right? So its mass of the system remains constant. So that is the mass conservation law, right? But this mass conservation law, like I had alluded to in the Reynolds transport theorem, is this axiom that you're familiar with, is essentially from a Lagrangian perspective or a closed system perspective, right? Or a systems approach. Now our job is to how can we transform this mass conservation axiom that we have from a system approach to a control volume approach so that now we can use it for fluids, right? So that's the goal here, right? So that's where the Reynolds transport theorem comes into play, right? So if you see here, right, the quantity that we are concerned with or the property that we are looking at is mass, right? So here B in this Reynolds transport theorem is nothing but mass of the system, right? So if we know that, okay, we can use that to rewrite this Reynolds transport theorem instead for an arbitrary, for a specific, for a quantity or property of fluid that is mass, right? So essentially we are saying that B of the system is nothing but mass in this case. So it's mass of the system, right? So if that is the case, what is small b? Remember, small b was nothing but capital B divided by m, right? So in this case, small b is nothing but 1, right? So now if you know what capital B is and if you know what small b is, all you have to do is substitute this into the Reynolds transport theorem. So substituting or subbing and small b into Reynolds transport theorem, right? So you had D instead of B of the system, you have M of the system now, divided by dt is equal to time rate of change of control volume, integral of control volume, rho. Okay, so you had small b, but small b is 1, so all you do is, so your small b becomes 1, and then you're integrating out over the volume, so you have this term, right? And the last term is just the flux of this quantity going in and out, right? So again, your small b is just 1, and then you have the velocity vector dotted with n dA. Okay, so you have transformed or rewritten Reynolds transport theorem specifically for mass, right? Instead of an arbitrary quantity, you have rewritten it specifically for mass. Okay, now that you have rewritten it, you use the fact that what does mass conservation law say, right? Mass conservation law or axiom just said, or we showed it in the previous slide, that this term is equal to 0 based off mass conservation, right? So if this term is equal to 0, you just substitute it here, right? And you get a new expression or you can simplify this expression of Reynolds transport theorem, right? So essentially, if I rewrite it, I will end up getting d dt rho dv plus cs, or plus integral of cs, or integral over the control surface rho v dot n dA is equal to 0, right? Essentially, this expression that you're getting here is the mass conservation for a fluid, a mass conservation law for a fluid. Fluid flow specifically, right? So this is what you use for a control volume approach. Okay. Okay. So now that we have this expression, or derived or found out this expression, like I've told previously, our goal is not necessarily, it's good to know the derivation, but at least from at this stage of being an undergraduate class, your goal is to mainly understand and remember or have a good sense of what this relationship means. That is the main goal to take away, right? If you know the derivation, that's better and great, but the bare minimum that you need to know is understand the relationships that are there. Okay. So what we'll try to do is we'll break down each term and see what each term stands and how it kind of relates to the mass conservation law, right? Or what it physically represents. Okay, so if we look at the first term here, okay, so the first term, that is this, right? So the first term, if you look at this, it's saying time rate of change of integral of rho dv, right? So let's just break it down into individual parts, right? So you have density integrated over volume, right? So if you have a certain volume and if you have some density distribution inside this volume, right, you're saying integrate density over this whole volume, right? So let's say, to make your life easier, if this density was constant throughout, what does rho dv end up being if your density was constant? So if rho is equal to constant, right? If rho is constant, then all it is rho times volume, right? This integral just becomes rho times volume, right? What is rho times volume? What is density times volume? Density times volume is nothing but mass, right? So this integral here, right, in this parenthesis, right, so this integral, right, all it represents is just mass of the material inside the control volume. So if you have this control volume, right, what is the net mass inside the material, right? Okay, so that's what this is representing, the integral, right? And then you're taking the time derivative of it, right? So essentially, if I want to rewrite it, right, this is dv, and now we just show that rho, the integral of rho over the volume is nothing but mass of the control volume. Okay, and then you're saying how is it changing with time. That is what this time derivative represents, right? Is it increasing with time? Is it decreasing with time? How fast is it increasing or how fast is it decreasing, right? So essentially, this expression here, all it is saying is the rate of change of total mass inside or in the control volume. Okay, I guess let me just rewrite this. Okay, so that is what I want you to take away and have an understanding, right? This mathematical expression is essentially describing how our mass or how fast or the rate of change of mass or net mass inside the control volume. So I want you to get an understanding of it so that when you're looking at problems, you can relate situations to this mathematical expression, go back and forth, right? If not, you'll start struggling. Okay, so this, hopefully this expression is clear of what it represents. Okay, next up we look at the second term that is there relating to mass flux. Okay, so now to look at the second term, right? The second term in the mass conservation equation represents mass flux, right? And I'll describe to you. So you have rho v dot n dA, right? So again, to kind of make your life simpler to understand this expression, right? Let's assume rho and v are a constant across a cross-sectional area. Right, so let's say if you have a pipe and you have flow coming across it, if this is your cross section, right, across this cross section rho and v are constant, right? So if this rho and v are constant, essentially this integral will just simplify to rho times v times area, right? So if this cross-sectional area is A. Okay, so what does this mean or what does this represent? Okay, so let's look at it slightly differently. So if this cross-sectional area, right, if you had this cross-section over here and let's say it had certain thickness, right, so you're looking at this cross-sectional area with a slight thickness, and this thickness or infinitesimal thickness was given by dx. Okay, and then the area of this cross-section is A. Okay. So if this is the case, right, what is A times dx? That is nothing but the volume or dV, volume of this cross section or this small slice that we have, right? Okay, so now if that is the case, what is rho times A times dx? That is nothing but rho times the small volume that you have of volume of this element that you have, and rho times the volume is nothing but mass. So it's mass of this element that you have here, right? It is mass of this element right here. Okay, so mass of the small element. Okay, if that is the case, now if you want to write the rate of change of mass, that is in this element, or this how the rate of change of mass, or how the mass is changing in the small element, right? So you're looking at dm dt. Let me just rewrite it so it's clear. So you have dm dt, right? So if you replace this or substitute this m as rho a dt, you have d dt rho a dx dt, right? So if you're assuming rho and a are not changing, this is just dx dt, right? What is dx dt? Distance or displacement or change of distance over time is nothing but velocity, right? So you have rho times a times v. Okay, so that is how this expression comes about of rho va, right? All it is saying is, when you're saying this, is if you have a cross section like this, the amount of mass passing through this cross-sectional area or entering through this cross-section can be any direction, right? So amount of mass passing through that cross-sectional area is being represented by this term. Okay, so this term here, the second term, all it does, it represents the amount of mass passing through or crossing the area, right? So in this case we are specifically looking at the area or the surface of the control volume, right? So it's control surface. So essentially it is saying the amount of mass passing through the boundaries of the control volume. Essentially that is the control surface, right? Okay, so one thing that probably you might be thinking, what does this v dot n represent? How is this coming out, right? So to better kind of explain this, I will make use of an example here, right? So mathematically, what does v dot n? You have two vectors and you have dotted it, right? So essentially this is magnitude of v times magnitude of n cosine theta. So that is the angle between these two vectors, right? That is the cosine, right? Okay, so let's say if you have a surface this, and we talked how n is the unit vector describing the surface, right? So that is n. So it's a unit vector, so its magnitude is 1. It's just essentially showing the direction of the vector, and you'll see what it is, how it comes into play. So let's say the velocity across the surface is in this direction, right? Okay, so this is your velocity vector. So there's a component in the y direction, vy, and there's a component in the x direction, vx, of this velocity vector. Okay, so vector v has an x and y component. Okay, so think about this surface being part of, let's say you have a pipe, and this is the surface we are talking. You're talking about the edge of this pipe, right? So this is the surface we are talking about here. So if this is the case, right, let's say if you had a flow that was going parallel to this cross-sectional area, right, so the velocity was in this y direction, right, will any of this air or water enter this pipe if it's going parallel to it? No, right? It will not enter the pipe, right? The ohm, right? Now on the flip side, if you have this cross section and now you have velocity going normal to it, to the cross section, right? So perpendicular to the surface itself. Now will this enter this cross section or will enter the pipe? Yes, right? So in this case it will enter the pipe, in this case it will not enter the pipe, right? Okay, so the only velocity or only component of velocity that you're concerned with that will enter the control volume or the surface or will cross through the cross sectional area is the velocity component normal to it, right? Okay, so that's why what we are doing here, right? What is the purpose of a dot product? Essentially we are saying we have this velocity vector, we want to take the component of velocity vector in the normal direction, right? That is what v dot n is doing, right? So if you have this velocity component, if you say this is theta between velocity and normal, by doing v dot n cosine theta, you are just taking this component in the same direction as velocity, right? So by doing this, you are kind of correcting for this component, right? So let's say if we had velocity going in this direction and normal to the surface, right? Okay, and n is 1 and then you have magnitude of v, right? What is vn cosine theta? What is theta between this? Right, it is in the same direction, so in this case theta is equal to 0, right? So vn is nothing but magnitude of v, right, times cosine, magnitude of n is 1, cosine theta is 1, right? So all it is saying is just magnitude of v. Okay, now if I erase this, make some space. Now what happens if your normal vector is in this direction, but instead of velocity being in this direction, it is on the opposite direction, right? Your velocity is going in this direction, right? So in this case, your theta is all the way from here to here, right? So that your theta is 180 degrees, right? So if you substitute into this expression, v dot n just becomes magnitude of v, the unit vector is 1, and then cosine 180 is minus 1, right? So all it becomes is minus this velocity vector, right? So what this v dot n expression is doing is accounting for the sign, right? So if you have a control volume, it is trying to figure out or is automatically accounting for if the mass is entering the control volume or is it leaving the control volume. Depending on that, it will make it either positive or negative, right? So that's the whole point of it. Okay. So now that we have kind of gone through individual expressions of what it is, I think so it will sink in more and more as we look at the simplified versions of this mass conservation equation or mass conservation law. Okay, so the mass conservation law essentially stated that the time rate of change of total mass in the control volume, sorry, I should write it as rho and this is dA plus the amount of mass entering or leaving the control volume needs to be 0, right? So if I rewrite this, right? I think so this will help you better understand by looking at an example, right? So if I take the second term to the right hand side, right, okay, so essentially what it's saying is the amount of change of mass inside the control volume, or the rate at which it changes, is equal to amount of, so this is saying amount of, let's say, I think it's more appropriate to say the rate of change of mass inside the control volume, right, is equal to, what does this represent? The amount of mass entering or leaving the control volume. The control volume through the control surface, right? So essentially through the boundaries, right? So that's all this expression is saying, okay? So for instance, I give this example of, it's a simple, very rudimentary example. If you have a bin, and let's say if you have 10 particles in it, 5, 6, 7, 8, 9, 10, right? Initially, if you had 10 particles in it, right? If I took out 4 particles, right? So I've took out 4 of these particles and then added 2, right? What is the mass inside this? What is the new mass? So initially M was 10. What is the new mass? The new mass is going to be whatever the initial mass was, but also depending on how much was taken out and how much was added, right? So that is what this adding and taking out is being represented by this second term, right? That is the flux. That is what the second term is saying. If you have an area, how much of mass is coming out and leaving it through that area, at what rate it is coming out and leaving it, right? So that is being represented by the second term. So you had 4 bulbs or 4 particles taken out and 2 added. So the net loss is 2, and that will determine what is the change in mass, in net mass inside the control volume, or how fast it's changing, right? So that's essentially the end goal here. Hopefully that it's clear and sinking in at this point, right? So similar to how we had Reynolds transport theorem, you can write this mass conservation for different types of control volume, right? So for instance, let's start with a general form of moving and deforming control volume, right? So in this case, your mass conservation will be rho dV. Remember, you cannot take the time derivative inside the integral, right? Or you cannot pull the integral outside, because the integral is changing, it is deforming, right? Plus Cs rho V, but now you're not using the velocity of the fluid, but you're using the relative velocity dot NdA, right? Because it's moving and deforming, and that is equal to 0. Okay, so now if you're looking at just a moving control volume, right, you can actually take the time derivative inside, so that you just have concerned with how the density is changing with time. Okay, and then the second term remains the same because you're still moving, so you are looking at relative velocity. Okay, so now if we were to do it for, you want to write the mass conservation for a deforming control volume, right? In this case, you have to ensure that the time derivative is outside, and then you are taking the integral of rho times dv plus the flux. Okay, and lastly, if you are doing, for simplest case of a fixed control volume, you can take the time derivative inside the integral, right, so that you are just concerned with the density, how is it changing with time, and since you are not moving, you are using the actual velocity of the fluid. You don't have to worry about the relative velocity. Okay, and next we'll look at how you can even further simplify some of these terms, especially for the fixed control volume, and then you'll see what is the benefit of moving this time derivative inside, right? How is it even helping you, or how is it making your life simpler? Okay, so let's say you are looking at a fixed control volume for a fluid whose density does not change, right? Which is a very common situation, right? Especially if you're looking at slow speed flows and flows of denser liquids such as water, right? So density of this water is constant. Okay, so if density of the water is constant, right? If you go and write this expression, it says that integral of control volume d dt rho dv, right? And then you have the second term that talks about the flux, or how much mass is entering or leaving the control volume, right? If density is constant, what happens to this derivative? Right? Derivative of a constant is, it is 0, right? So this term will drop off, and since integral of a 0 is 0, essentially you can cancel this whole term, right? So even though, let's say, the mere fact that the volume is remaining constant, and for most cases that you might be encountering, your density of fluid is constant, right? You can completely drop off the first term, right? And your problem has become so much simpler. All it is saying now is the amount of mass entering, or the rate at which mass enters the control volume, should equal to the rate at which it leaves the control volume, right? Because nothing can be accumulated inside it, right? Because there's no net change in mass, right? Okay, so that's essentially what is being said. This scenario of density being constant is called as an incompressible flow, right? Okay, so another form or another simplification sometimes we can do to the fixed control volume mass conservation equation is for 1D inlets and outlets. Okay, so what does, first let's briefly say what does 1D inlet and outlet mean, right? So essentially, if you have, let's say, a control volume, your control volume is a tank, and then you have two inlets and outlets here, right? Essentially, it is saying that your velocity is in the same direction as the normal vector, right? It can be, so there is no component or theta degree, so it's either 90 degrees or sorry, it's either 0 degrees or 180 degrees, right? So let's say if you have a velocity or mass coming in, right, and here the mass is going out, right? So essentially you're saying one of the criterias for inlet and outlet to be 1D is that the velocity vector is parallel to the normal vector, right? So it is either the theta degrees is either 0 or 180, 0 degrees or 180 degrees, right? So this is the case, right? The other requirement for it to behave as a 1D inlet and outlet is the fact that the velocity across this, so if I want to zoom into this, right, so the velocity across this cross section is constant, or you know what is the average velocity, right? So essentially if this is a pipe, yeah, so across this velocity is constant, so that is the other criteria that you need, right? So the velocity that you're considering is constant across the cross section of the inlet and outlet. So this fact that if you have a 1D inlet outlet, it helps you simplify your mass conservation equation, where the second term you don't need to integrate or have an integral. You can simplify it into just a product term, right? So the first term remains the same, but for the second term, right, you can just write it as a sum of the product of density times area times velocity. So essentially mass flux of all of the quantities, you can add them up, of leaving, that is leaving the control volume, and then minus sum of all of the terms or all of the quantities of mass flux entering the control volume. Right, so this simplification allows you to get rid of doing any integration in this sense, right, at the inlets and outlets. Okay. So to further go through that, right, this rho times area times velocity is known as mass flux. This mass flux is often given as m dot, right? Okay, you will sometimes see that this can be instead of mass flux, so if you divide mass flux by density, right, all you get is area times velocity, which is known as the volume flux or flow rate or volumetric flow rate. Okay, so that's a further simplification you can make, right? So if you want to quickly look at how that expression works, okay, so to quickly look at how this expression works for 1D inlet and outlet. I think it's best explained with an example. Oh, I think it's minus. So let's see if an example, you have a container and now you have multiple inlets and outlets, right? So essentially, let's say you have mass flux m dot 2 coming out from here, you have m dot 3 actually entering the container, you have another one m dot 4 coming out, and some mass flux coming in, right? So this expression is the same as we can write it in terms of like we said, rho AV is nothing but mass flux. So this is essentially, we can also rewrite it as terms of CV ddt rho dV plus summation of I m dot of I of out minus summation of I of mass fluxes coming in, right? So we are just separating mass fluxes coming in versus mass fluxes coming and leaving the system, right? Just to simplify things. Okay, so essentially, what if we want to do this, we are adding up or clubbing up all of the ins and outs, right? So the summation of I mi mass flux of I coming out is nothing but, which are the ones coming out? M dot 2 is coming out of the system, and then m dot 4 is coming out of the system, right? So these just gets added up, right? And then summation of I m dot I of n, which are the two that is coming in? M1 is coming in and M3 is coming into the system, right? So M dot 1 plus M dot 3, right? So all that it says is that add up all the mass fluxes coming in to the system and subtract that from the sum of all the mass fluxes going out of the system. That's all that is saying. Okay. So if on top of it, so next form of simplification is, if on top of this, if you had a steady flow, right? If you had a steady flow, what was the definition of a steady flow? The definition of a steady flow was that none of the flow properties would change with time, right? So flow properties or parameters do not change with time, change with respect to time, right? So time part is very important, right? Okay, so you have this expression of CV ddt rho dV plus summation of mass flux out minus mass flux n is equal to 0, right? But now you're saying that it's a steady flow and nothing is changing with time, so there is not going to be any time dependency, right? So the flow or none of the quantities respect to the flow is changing with time, so this term will drop off. So essentially all that your mass flux says or mass conservation says is the net amount of mass coming in or leaving the system should be equal to the net amount of mass coming into the system, right? So this becomes further simplification of the mass conservation law. Okay, so now that we have gone through different forms of mass conservation law and different steps, next we'll go through example problems to kind of drive in these concepts and understand. So a combination of example problems and homework problems will help you, hopefully help you understand and absorb these concepts. Okay, so now we'll go through some example problems that will help better understand the mass conservation law. So the first example problem. Okay, this is essentially you have a nozzle, let's say, where the air cross-sectional area is changing and it's reducing. Right, you have a flow coming in and the velocity of this fluid flow coming into the nozzle is, let's say, 33 meters per second. Sorry. Okay, the area of cross section at this inlet is 10 meters square. Okay, now the area of this outlet is given to be, we'll do three parts of this problem, or three sections in some sense. So in the first case, the area is given to be 5 meters square of this outlet. In the second part, we want to find out what the area is, 2 meters square. In the third part, the area is 1 meter square, A2 of the outlet, right? Our goal here is to find the velocity of the fluid coming out. What is this velocity coming out of the outlet, right? Okay, so intuitively, we kind of knew, and we have talked about how if the area is decreasing, mass conservation dictates that the velocity would increase, right? That's the whole principle between water hose being, you squeeze the water hose for the water to go further off, right? The projectile distance to increase. So what we are doing here is this simple intuitive problem. We are trying to prove it using mass conservation. Okay, so if this is the question, so the things that have been given to you is, one, you have been given the area of the inlet, which is 10 meters square. Two, you have been given the velocity of the inlet, which is 33 meter per second. And third, you have been given area 2, which you have been given three cases. So you have to find the velocity for three different options of area 2, right? So in the first case, the area 2 is 5 meters square. Second case is 2 meters square, and in the third case, area 2 is 1 meter square. Okay, now what you have been asked to find is the velocity of the outlet, so let's say V2, for these corresponding to these three different cases that of area that you have, right? So your question is to find V2. Okay, first off, right, our goal here is to find V2. So the first thing you would want to do is figure out what the control volume is and what type of control volume you have, right? So in this case, you're dealing with water coming into the nozzle or air coming into the nozzle at a certain speed and exiting, right? So if the system or the control volume that you're looking at has to be just this nozzle, right? So your control, so you draw your control volume such that it surrounds the nozzle. Okay, so that is a control volume. Now the question always, like we talked about before, is right. If your first thing is to identify what the control volume is, and then next identify what type of control volume is, right? So always when we talked about control volume, we talked about the two questions you need to ask yourself: is the control volume moving, and is it deforming? Okay. So in this case, since this is a nozzle and a rigid nozzle, it's not deforming, right? So control volume is not deforming. And since it's a nozzle, it's safe to assume that it is not moving even. Right? So hence this is a type of fixed control volume. Right? So you can probably mention this in your assumptions. Okay, that it is not deforming. So control volume is not deforming, control volume not moving. Hence it's a fixed control volume. Okay, what are the couple other assumptions you can make, right? You can assume that the fluid is incompressible, so the density is not changing of the fluid, right? It remains constant. Unless explicitly said, for most of this fluid class, you can assume that the density is constant, unless explicitly said, right? So that means if the density is constant, rho is constant, hence the fluid is incompressible. Okay. What is something else you can say, although it has not been explicitly mentioned? So if I ask you, right, that is one of the questions that you have to answer is the fluid or the flow characteristic or flow parameters changing with time, right? So in this case, what do you say, right? We discussed this previously, right? The velocity is changing, but the velocity is changing with respect to space, not with time, right? At any given location, if you check the velocity at different time intervals, it will be the same, right? Hence the velocity is not changing with time. That means you can assume you have a steady state or a steady flow. Okay, so if this is the case, right, you can now proceed with mass conservation to try and solve this problem. Now, in your case, you just have one outlet and one inlet, right? So the outlet is given by the variable 2, so that is mass flux coming out, should equal to the mass flux coming in. Okay, sorry, I should write it as 1. That's the variable that we've used. I'll just rewrite it. Okay. So what had we previously mentioned? How can you compute, or what's the relationship for finding mass flux? Right, mass flux is given by just rho, that is the density of the fluid, area times the velocity. Okay, so essentially this can be rewritten as density of the fluid, area of the inlet times velocity of the inlet is equal to, on this side for outlet you have density of the outlet, area of the outlet, and velocity of the outlet, right? Since the density is constant and uniform, your density can be cancelled off. So essentially, right, your area times velocity is going to be balanced, right? So essentially your volumetric flow rate, or flow rate, is balanced. Hence, you can rewrite it such that you can find the velocity, which is nothing but V1 times area 1 by area 2. Okay, so essentially the velocity of 2 is related to the ratio of the areas of the inlet and outlet. Okay, that's what this is stating. Okay, so you get this relationship directly from using mass conservation, right? So now if you see, the smaller the area 2 is, right, the bigger the velocity is. So smaller area 2 with relation to area 1, the bigger the velocity is, right? So essentially that's kind of what we have been saying while we have given this example of a nozzle. Okay, so for the first case, right, now that we have this relationship, in the first case, right, we were told that the area of the outlet is 5 meters square. So if you substitute it into here, V2 is equal to V1. Your V1 was 33 meters per second. Your area 1 was 10 meters square, and you divided by 5 meters square. Right? So this should be simple mathematical or simple algebra. 5 by 10 by 5 is 2. So this comes out to be 66 meters per second, right? So that's as straightforward as that, right? So velocity comes out to be 66 meters per second. Okay, so now you were given, so you got the answer for the first part, right? Now you have the second part where the inlet velocity stays the same and the area of the inlet stays the same. Now the outlet is further converged or reduced in size, right? So essentially we are trying to see what happens if we are constantly reducing the size of this outlet or the area of the outlet, right? So we reduce the area to 2 meters square, right? So if we go back to this relationship, you have V2 is equal to 33 times 10 for area 1 divided by 2. So this becomes 5, right? So you have 165 meters per second. Your velocity of the outlet would be 165 meters per second. Okay, so we got the answer or solution for the second part. Now if you do the third part, okay, so third part states that the area 2 is 1 meter square, right? So now if I go back and plug this into this relationship, you have V2 is equal to 33 into 10 divided by 1, right, which will give me 330 meters per second velocity, right? Okay. So my question for this third part is this: if this answer is correct, right? Is this answer or the calculation you did, is this correct or wrong, right? So if this is a correct thing that you did or a wrong thing that you did, right? And this whole third part was put in essentially to highlight the reasons of always keeping in mind the assumptions that you there, right? If you would have actually done a test, let's say of if it was air coming into the nozzle, you would see that you are probably not going to get 330 meters per second at V2, right? You're not going to be able, so your calculation is somehow wrong, right? So the question is, what is the issue? What break down? Okay, so the breakdown essentially stems from one other fact, which I guess I should pose as a question first, is, do you guys know what is the speed of sound of air? Or at least roughly, right? So speed of sound in air is actually approximately 330 meters per second, right? Which is exactly the value that you have here, V2, right? So that means the Mach number, hopefully you have heard of this number called as Mach number, right? If you have heard about supersonic flights, if you watch Top Gun, they always talk about Mach number, right, as a speed of the aircraft, right? Mach number is essentially a ratio of the velocity of the aircraft or the fluid divided by the local speed of sound, right? So let's say if your velocity in this case is 330 divided by the speed of sound, right, essentially you are at Mach 1. The reason Mach number is the reason where you provide speeds of aircraft in Mach number and why it is important is because of what happens physically to the fluid when you're at close to Mach number 1 or above or equal to or exceeding Mach number 1, right? When you're close to Mach number equal to 1, your fluid can no longer be assumed to be compressible. The fluid becomes compressible or behaves like compressible fluid, right? Essentially meaning that at Mach number 1, your density, so if you reach close to Mach number 1, your density is no longer constant, right? Okay, so if your density is no longer constant, this whole relationship that you had come up or we came up with, right, or V2 is equal to V1 times A1 by A2, right, this whole relationship was derived based on the fact that the density is constant, right? Now since the density is not constant, this relationship does not hold true anymore, right? And this is the whole point of trying to just be mindful of the assumption that goes to it, right? Sometimes it's explicit assumptions, sometimes they're implicit assumptions that you make always in any problem, right? So this kind of just shows to or helps to reiterate the fact or the importance of always writing down the assumptions, or at least be aware of the assumptions that you're making in any given problem, right? So essentially this relationship you cannot use, or this derivation or simplification we did cannot be used at these speeds, because the Mach number is close to 1, which leaves the density is no longer constant, right? Okay, so as the fluid progresses, it keeps on accelerating, and as a result of that acceleration getting to speeds close to Mach 1, your density changes spatially as well, right? So that's kind of the point here. Okay, with this being done, we'll move on to the next example problem. Now, the second example problem is just a small variation of the first one. So essentially, in the first example problem, we assumed that the nozzle is stationary, but now if you consider the nozzle to be part of, let's say, a rocket engine, and it's moving on its flight, right? So the engine itself and the nozzle is no longer stationary, but let's assume, to make life simpler, is moving with a constant velocity, right? So you have the same kind of nozzle, everything else remains the same. So you have this air coming at 33 meters per second. This cross-sectional area is 5 meters square. Oh, sorry, this is 10 meters square, my bad. This outlet area, there are 3 cases of it. The first one, it is 5 meters square. Second one, it is 2 meters square. And the third one is 1 meter square. Right. But now, like we said, the nozzle is moving. And the velocity with which the nozzle is moving, let's say it is 10 meters per second. Okay, and the given direction, right? So it's moving against the direction of the incoming airflow. Okay. And essentially you need to find the velocity v2. That is the question. So everything is the same except for the fact that your nozzle is now moving with this velocity, right? So the whole point of this is to identify the control volume, right, of this example. So your control volume is again just the nozzle, so you have to mark it, right? You are marking with the dashed line, right? Now the question is what type of control volume it is. Okay, so if you are tracking this nozzle, right, you cannot be at zero velocity anymore because the nozzle itself is moving, right? So this nozzle is an example of a moving control volume. Okay, so it's an example of a moving control volume. And what is the how does the mass conservation law get modified when you're using a moving control volume, right? So the main difference that comes about when you're using a moving control volume is the fact that when you're using velocity, right, so your mass conservation law was d dt. Let me rewrite it with some space here. Integral rho dv plus integral of c. So the first term represents the time rate of change of mass inside the control volume, and then the second term is the flux, right? Control surface, so it is rho v dot n dA, right? But the biggest difference is this VR, right? It is no longer V. So you use relative velocity instead of absolute velocity in this case, right? So essentially, if you go through the simplifications like we went in the previous problem, right, you will end up finding that your mass flux at 1, or the outlet or inlet, sorry, should equal to the mass flux at the outlet, right? But now when you're writing the mass flux, it is no longer rho a v, it is rho a relative velocity at 1 and is equal to rho area 2 of relative velocity of 2, right? So this cancels out. Okay, so the area 1 is 10 meters square, right, times the relative velocity times area. Actually, we can keep it, go from here. Area 2 is 5 meters square, and then the relative velocity at 2. Okay, so the point is, how do you write relative velocity? Right, relative velocity was given as, right, relative velocity vector was given as velocity of the fluid minus the velocity of the control surface, right? So in this case, if you're finding velocity r1, okay, so that is 10 times, what is the velocity of the fluid, right? It is in a positive direction. Actually, this should be vectorial, so I should put dashes on top of these, right? So the velocity of 33 meters per second is in positive direction, minus the control velocity of the control surface or control volume, so minus the velocity of the control surface, but the velocity of the control surface in the opposite direction. So this is, so if you remember, just so that you have it on one side, right? So you have 33 in this direction, and this is moving, this control volume or control surface moving with 10 meters per second, right? So if this is a positive x direction, right, 33 is in the positive direction, but 10 is in the negative. So this is minus 10 is equal to 5 times the relative velocity over here. Okay, so if you want to find the absolute velocity out here, so then you have to do the same thing. V2, if your thing is in the positive direction, and then you'll have minus 10. Okay, so now if you simplify this, you see you get 10, sorry, it is not plus, it is 10, 33 plus 10, right? So these velocities gets added up because it's moving in opposite direction. Okay, and the same thing here, you have V2 plus 10. Okay, so finally, if you simplify or do the math, essentially you get 10 times 43 is equal to 5 times V2 plus 10, right? So 5 and 10 can cancel off and simplify to 2. So you essentially get V2 is 43 times 2 and then minus 10. It's a 2 4 is 8, 2 3 is 6. Okay, so as you can see, this value ends up being different, or velocity of the value ends up being different than that of the first example. Okay, and actually it is greater than the velocity in the first example, and partly because of the fact that the nozzle is moving in opposite direction of intake, right? So essentially, since it's moving in the opposite direction of the inlet velocity, you get from the relative velocity perspective, you get a more faster velocity coming in, right? It's a higher amount of air coming in as a result, right? So this is kind of some of the principles they use in aircraft engine, and especially if you look at scramjet or ramjet engines, if you've heard of that, right? Those are engines that have aircraft engines that have no moving parts and are used for hypersonic aircrafts. Like probably the one you saw if you've seen Top Gun movie, right? They show you a hypersonic aircraft which has no moving parts. So the way it compresses the air is by moving at a velocity in the opposite direction. So you get an increased incoming flow into the engine inlet. Okay. Okay, so now we'll try a different problem. I'll go through a different example problem. So here you're essentially filling up a balloon with air, with an air intake, right? So you have the density of air coming in at a certain velocity v1. You know the inlet size of this, which is given as area 1. Okay, and this is getting into this balloon, right? So it can so if you have ever filled a balloon, you know it stretches and fills up and increases in size, right? Density inside this balloon, because the pressure would increase, right, can change with time. And the radius also of this balloon obviously will change with time. Okay, so the question that you being asked is, given these inputs, the first is to find the rate of change of mass of air in the balloon. So as it is getting filled up, what is the rate of change of air inside the balloon, right? The second question is, if you assume, in this second part only, if you assume density inside the balloon is a constant, then what is the rate of change of radius of the balloon. Okay, so the whole reason of doing this problem is to emphasize again on the type of control volume and how things change if there's a different type of control volume, right? So again, as always, first thing what you want to do is identify what the control volume is, right? So your control volume in this case will be just the balloon with this inlet in it, right? Okay, so you can have the inlet as part of it or just do it the way I have done it, as long as you account for the velocity, right? So this is your control volume. The question is, what type of control volume is this, right? So what is the type of control volume it is, right? Like always, the two questions that you have to ask yourself: is it moving or is it deforming, right? So there is no net velocity or global velocity to this to this balloon, right? The balloon is fixed to the air inlet that is filling up air inside the balloon, right? So it's not moving anywhere, but naturally it is expanding. So that means it's deforming, right? The shape changes constantly, the volume changes constantly, right? As a result, this is a deforming control volume. Okay, so this is an example of a deforming type of control volume. Okay, so now if you go to the mass conservation law, one of the key things that you have to remember is, in this case, you cannot pull the integral out or the time derivative inside, right? Because the control volume itself or the integral is changing with time, right? So this integral has to be inside the time derivative when you're finding the total rate of change of mass. Okay, and then you have the inlet is a 1D inlet, so you can simplify it into mass flux out minus mass flux, let's say out minus mass flux in is equal to 0. There is no outlet, right? So there is no mass flux out. There is only mass flux coming into the system, right? Okay, and so if you want to further simplify this, right, you have to rewrite it, the volume. So how do you find the volume of this of this sphere, right? Of this varying sphere size, right? So balloon is generally like we can assume it to be the size of a shape of a sphere to make our life simpler, right? So essentially you can rewrite the volume or the control volume. Let me just change this. So instead of the volume, we will rewrite it in terms of the surface area 4 pi r squared times the thickness of the volume, right? So times dr. Okay, so essentially you have changed the volume integral into in terms of radius. Okay, so that should be straightforward, and then the m dot n is nothing but rho 1 a1 v1, which you know about it, right? If you go ahead and integrate this, right, rho is a function of time. If you assume rho to be a function of just time, then you can integrate this, and essentially it will come out to be rho t is equal to 4/3 pi r cube, which is nothing but the volume of a sphere, right? But this radius is also a function of time, and then you end up getting this is equal to rho 1 a1 v1, right? So density times the volume, what is it? It's nothing but just the mass, right? So for the first step or the first problem, right, you didn't have to integrate at all. You could have noticed or identified that this integral is just the total mass of the system, right? So the first step for the first problem or the first question, you could have directly found the rate of change of mass, which is ddt, time rate of change of mass is given as this expression, right? That's the first part, is equal to rho 1 a1 v1, right? Okay, because everything we found out inside the integral is just mass, right? Always remember where we started off with, right? Now for the second problem is where the simplification, second part is where the simplification helps, right? ddt or mass, right? We just computed, it is written, you can rewrite it as rho of t times 4/3 pi r cube, which is also a function of time. Okay, is equal to rho 1 a1 v1, right? So then the second part, we have made the assumption to make our life slightly easier or calculation easier, that density is a constant. Okay, so density of air inside is constant. Okay, so in that case, what is the rate of change of radius, right? So since rho and 4/3 and pi is constant, you can take it outside the integral, outside the derivative. So you have 4/3 pi times rho, okay, d dt of r cube. Okay, so now if you bring this 4/3 pi here, and you just need to take this derivative, right? So essentially, if you take the derivative, it will come out to be 3r squared t times dr dt is equal to rho 1 a1 v1 by rho by 4/3 pi. Okay, so essentially you can end up, if you move this around here as well, what you end up getting is a relationship for dr dt, which is the time rate of change of radius, right? So the whole point of this example was to make you understand and realize that when you're dealing with a deforming control volume, you cannot take the time derivative inside the integral, because the integral itself, or integral of the control volume itself, is changing with time, right? So you have to make sure that you are taking the time derivative of accounting for the time derivative change, the rate of change of that volume as well, right? So whenever there is a control volume that is changing, that is changing with time, that essentially is a deforming control volume, then make sure that you're accounting for that change by keeping the time derivative outside the integral. Okay. Okay, so the last example essentially is that of a tank which has two inlets. Okay, so you have water coming in from two inlets, right? Uh, you have been given the cross-sectional area of the tank. You have been given the velocity and diameter of these two inlets. Your goal is to find the rate of change of height of water in this tank. Okay, so again, so first thing you would want to do, or I want to make sure that you understand, and I would expect you to do in all your examples and homeworks and exams, is to show first what is the control volume that you are choosing, right? So in this case, your control volume will encompass this liquid contained in the tank with the boundaries of the two inlets and the height being changing with time. Okay, so if this is changing with time, the control volume's shape is changing, or the volume is changing with time, hence it's a deforming type of control volume. Okay, so if it's deforming, we went through this in the previous problem, you have to make sure that the time derivative, when you're using the mass conservation law, it's outside the integral. For the first term, right, this inlet and outlet, I should have written the given, you can assume it to be 1D, right? So if it's 1D, you have sum of all the outlets, mass flux of all the outlets minus sum of mass flux of all the inlets is equal to 0. Okay, so this is the relationship or the equation that you're going to use to solve this problem, right? Okay, couple other things that have been given to you, like I said previously, is the diameter. So you've been given the diameter d1, let's say it is 1 meter, the diameter d2 is 2 meter. You've been given the velocity v1 as 2 meters per second and velocity v2 as 5 meters per second. The area of the tank, or the cross-sectional area of the tank, is given to be 10 meters square. Okay, so from here on it should be straightforward a bit. Okay, so your first term, right, is d dt cv rho dv, right? Okay, and then the second term, there is no outlet, right? So this term essentially goes to zeros, and there's no outlet. There are two inlets, which is m1. Let me just write it in. M dot 1. So sum of the two inlets and m dot 2 is equal to 0, right? So since density is not changing here, right, so you can assume it to be incompressible because it's water and it's not at moving at high velocities. You have rho can be taken out of this integral and the time derivative because density is constant, right? So you have d dt of this integral of cv dv, and I'm just breaking it down into further steps so that you clearly see what's happening. And then you have the mass flux of the two inlets, so it is rho 1 a1 v1 plus rho 2 a2 v2 is equal to 0. And hopefully you realize that it's water that is coming in, so rho 1 equals to rho 2 is equal to rho, so you can cancel that terms out. Okay, so once you have done that, then you have to integrate this. Integral of this is just the volume, right? So d dt of the volume of fluid in the tank is equal to minus, or if you can put it as is equal to a1 v1 if you take it to the right hand side, plus a2 v2. Okay, so now if you rewrite what the volume of the tank of water in the tank is, d dt, the volume is nothing but the area times the height, which is changing with time, and that is the sum of a1 v1 plus a2 v2. Right, since this area is constant, the time rate of change of height, you can take the area out, is just a1 v1 plus a2 v2 divided by this area of the tank. Okay, so essentially you have been able to find the expression for the rate of change of height of water column in that tank, right? So essentially this becomes your answer, right? You just need to plug in the values there and you'll get the answer, right? Okay, so the whole reason to emphasize for this problem was you've already tackled a problem with a deforming control volume, right? So this is very similar, but the fact that if something is changing with time or if something is changing is relative in sense, right? It's sometimes like how fast is it changing, right? So in this case, the area of the tank was comparable to A1 and A2, right? So in that case, the rate of change of H is going to be quantifiable, is something that is tangible, right? But now say if you have an inlet coming in, or if it's an outlet, right? But the area of the tank is no longer a tank, but it's like a lake or a reservoir of a hydroelectric plant, right? Or it's just a massive lake, right? Even if you start dumping water, so let's say if you have a lake and if you're dumping water from your hose, right? What is the rate at which the height change, right? So in that case, essentially, let's say your hose is, we have just one inlet, so just to simplify things so that you can see. So let's say if you just had one inlet, so you have A1 V1 divided by this area of the reservoir or tank or lake, right? But let's say if your area of the reservoir was, let's say, 10,000 meters square, right? And you have a hose, so it's a small hose, right? So it has an area of, let's say, 0.01 meters square, right? So if you plug it in here, you'll see 0.01 times whatever the velocity is divided by 10,000, right? When you end up dividing this, you'll see that this value ends up becoming very small. That is that you can approximate it to be 0, right? It will be significantly smaller, right? And that's the whole point, is the fact that if the area of the tank or the reservoir is massive, right, the height or the level of lake water in it it's in theoretical point of view, it is changing, but it is changing at a very small rate that it can be assumed to be stationary completely, right? So essentially, in that case, right, you can assume it to be not a deforming control volume, or you can assume it to be something that is not changing with time, so it's a steady problem, right? So that's something you have to be mindful of when you're using this for homework exams or even for practical applications, more so for practical applications. Like, can you make the approximation, can you make the assumption that it is a steady problem or it's a deforming, right? Depending on what is given. So intuitively it makes sense. Here you are saying mathematically that it makes sense, right? Because that will significantly simplify your calculations, right? Okay, so that pretty much brings us to the end of this mass conservation law. I will not be reviewing or do a review slides for this separately for mass conservation. What I generally do is I do momentum conservation after this, and I review mass and momentum conservation together, as you'll see how there is a lot of overlap, right? So you can see the connection. That's part of the reason I do it together. Okay, so yes, so next up we'll start up with momentum conservation.